Hello, everybody, and welcome to, this says Algebra 2.2, but it's really Algebra 2.3, Unit 8, Lesson 8-1. So this is your introduction to exponential and logarithmic functions. And people often get a little distressed about these. I'm hoping that I can help make it not quite so distressing. And so we're going to jump in. Okay, so the first thing, you guys are familiar with exponents, right? So if I see like a number 1 here, I have 7 to the 5th power. Hopefully that's something that you guys are like, oh yes, I see that. And this has 2 parts. It has the big number part and the little number part. So the little number, you guys probably all know, is called the exponent. The big number is called the base. Which you may or may not know, but this term, that the big number part of an exponential expression is called the base, is going to end up being super important to everything that we're doing. So hopefully that's something that you can kind of get a feel for fairly quickly. Okay? All right, so let's look at some stuff, and you're going to be like, why are we doing this? It will all become clear soon, I promise, okay? So we're going to ignore exponential and logarithmic functions for a moment and start by just talking about inverses. So inverse is like the opposite, right? Okay, so if I say, hey, what's the opposite of addition? You'd be like, well, duh, Miss Shock, it's subtraction. Okay, and what you then probably don't think so much about is exactly what that means. So what that means is we start with something, in this case, x, all right? And we add a thing to it, and we get some sort of answer. So what does it mean that subtraction is the inverse? Well, what it means is that if we take that answer and we subtract the thing that we added, then we end up with where we started. Okay, and that's going to be really important. This idea that, like, okay, the like opposite of something lets me take my answer and do a thing and get right back to where I started, right? So you can see, right, we started with x, and for addition, we end with x for subtraction, okay? So multiplication, again, probably super easy, right? So we start with x, some number, right? Then we multiply it by a thing, and we get an answer. So then if we divide, division, then we can take that answer and divide it by the thing. Ooh, this should say thing. And we get right back to where we started. We get right back to that x, okay? So now, so addition, subtraction, multiplication, division are relatively easy to imagine with your brain. So imagine I gave you a large pile of things, okay? And I said, okay, show me addition with these things. You'd probably like make 2 little piles and be like, okay, when I add them, I put them all together. And then like there are this many in this pile and this many in this pile. And now I just count all of them, and that's addition, right? Subtraction would be, all right, so here's a pile, and I'm going to take away some number, and now I count what's left, and that's subtraction, right? Multiplication, you would say, okay, I made a little pile, and now I'm going to make more piles that are the same size and count them all up. That's what multiplication is. Division, you take a big pile, and you divide them up into groups of however many, and then you count up the number of groups, and that's division. So it's fairly easy to in your mind, understand, like truly understand addition, subtraction, multiplication, and division. Like, what are those? You guys probably have a pretty good understanding of those. For exponents, it might be a little bit more difficult. So we have an x raised to something, and we get an answer. So what's the opposite of this? How would I get back to x using my answer and the thing? Well, think about if you had like, you don't need to write this down. If you had like x squared equals 9, how could you do that problem? You could think with your brain, oh, I know that 3 squared is 9. If I like change this to like 94, so now like you don't know what you square to get 94, you could still take the square root of both sides to get 90 to get what x would be. if you have a higher exponent, so like let's say I say x to the 5th is 94, instead, you don't take the square root, you take the 5th root. So you'd say, hey, whatever the 5th root of 94 is, and you show 5th root by putting a little 5 in the little sort of crook of the arm of the square root sign. So that would be how you would get the 5th root of 94. And it's some decimal, it's some number, who knows what number, you know, your calculator knows. So the inverse of exponents are roots, right? So if you want to solve for the base, get rid of the exponent and solve for the base, you take the root of something. So it is the whatever, the thing root, whatever that exponent is. Okay, the thing root of the answer will get you back to x. Okay, this says answer. Answer. My thing is being a little slow right now. Okay, so this is harder to visualize, right? So if I give you like a pile of things, visualizing the exponent and the square root is much more difficult to imagine. You could, in theory, visualize roots by like you take your pile and you make it into a square and you kind of deal with any leftovers you have, but it's a lot more complicated and not nearly as intuitive. But what I want you to understand is you don't generally have a problem with the fact that square roots and stuff exist, right? You're like, I press a button on my calculator and it does it, okay? And if you have an easy one, like if I say x squared is 25, you probably don't press a button on your calculator. You probably go, oh, hey, it's x would be 5 or -5 because that's what I square to get my answer. So what we're going to look at now is a similar thing. Okay, so notice that what's going on here, okay, is that now I am going to solve not for my base, but I'm going to solve for the exponent itself, okay? So if I need to get rid of the base so that I can get the exponent, this is called a logarithm. And the whole point of logarithms, the whole point of them is it's what you do to the base to solve for the exponent. That's what they are, just like the whole point of square roots is it's what you do to a number to solve for the base, okay? So the way that logarithms work is you write log, L-O-G, that's an L, okay? Base thing. So the base, remember I said the like big number of the exponential expression is a base. So the way that you write it is you write it like small, like you would write an exponent is small, but above, like the base is small, but below. Okay, so log base thing of the answer, right? Because remember in inverses, we do something to the answer equals the exponent equals x. Okay, so the same thing, it's the same thing here where you're kind of thinking about like, okay, what can I like, what exponent could I use to get an answer? So let me give you a similar example to sort of what we started out with. Okay, if I tell you that 3 squared is 9, oops, that's not what I was supposed to do. If I tell you that 3 to the x power is 9, you're like, oh, hey, x is 2 because 3 squared is 9. If I tell you that 3 to the x is 94, you can't take the xth root of both sides. That's not a thing, okay? So what you would have to do is you'd have to set up a logarithm in order to solve for this x. And so that's what we're going to be doing, is we're going to figure out how to solve for exponents, okay? So the rule that relates exponential equations and logarithms, this is what you're going to come back to over and over and over. So this is like the most important thing that you can possibly have. That's probably actually going to be really annoying, is this right here, okay? So the equation, the rule that relates them is if you have a base raised to an exponent equals something, the answer, I'm going to call that the answer, then the log base b of that answer, and this can go in parentheses or not. A lot of times it doesn't go in parentheses, equals the exponent. So let's use some color there to help you sort of see what's going on, okay? So I'm going to start with, okay, my base, oh, it's not going to be green because that's real hard to see on that green. Okay, so my base will be this color. So if I have my base raised to an exponent equals my answer, then if I'm changing that into a logarithm, the base is the little number that goes below the log. The exponent, let's do this, up here, okay, is what the logarithm equals. Okay, so it always equals the exponent. Logarithms equal the exponent. You'll hear something like log is power, because like power is another word for exponent. So if you are trying to remember it, right, so the logarithm always equals the exponent. And then sort of the base and the exponent are the two things that you're really going to like super pay attention to. And then whatever's left over, so the answer is what you take the logarithm of. So it's a little complicated calling it answer. I know that can be a little bit confusing because it's like the answer of the exponential expression, but it's not the answer of the logarithmic expression. So argument is another name that it can be called. There just isn't a great other way to say it, because the base and the exponent are always what they are, and then sort of whatever you have left over is the thing that you're taking the logarithm base b of. Okay, so we're going to talk about this more in a minute. It'll probably make more sense once you actually see some examples. Okay, but before we do that, okay, so the base of a, like the base is probably the most important part. It's like the first thing that you want to recognize. Okay, so the base of a logarithm, is the same as the base of an exponential expression. You can just say an exponent is fine, even though that's not quite right. Exponential expression is really what you want, right? So logarithm, you have like log base b of some stuff is the same thing as like b raised to the stuff. Okay, so recognizing that, and let me just get the same colors here. Okay, so recognizing that this place, like the little number in the logarithmic expression, is the same as the like big number raised to the exponent in the exponential expression, is going to be sort of the foundation of how you're going to do these problems. Okay, so let's go ahead and jump in to some examples. Okay, so this first one, we have 5 to the third power equals 125. That is a true statement. You don't have to do anything with it. You're not like putting anything into the calculator or anything like that. Okay, so let's look at what each thing is. Okay, so first of all, the base is 5. Okay, the exponent is 3, and the answer is 125. So you probably want to have written down somewhere that you can see it. So when you keep going back and forth, that that rule. So the rule is that if you have, let me scroll up just a little bit here and I'll write it above here. Okay, so it's on the previous page here, but it's that if I have b to the x equals a, then that tells me that log base b of a equals x. And again, you can put this in parentheses, that a in parentheses or not, it doesn't really matter. Okay, so I'll put the highlighting back on, right? Okay, so we have an exponential expression here. So first we have the b, right? So the base is 5 in this exponential expression. So when we write our answer, we're going to have log base 5, right? So it's a little 5 that kind of goes right down below. Okay, so so that's our base, right? Okay, so then the next thing that we have in our exponential expression is the exponent. Okay, so we have the 3, right? Okay, so that's the exponent. And so the exponent is what a logarithm equals. Okay, so I'm going to leave some space here for a and say, okay, it's going to equal my exponent, which is 3. And then finally, we have the answer or argument or whatever, right? And that's what we're taking the logarithm of. So it's going to be 125 right there. So log base 5 of 125 equals 3. This is our answer. That we're not like doing anything to it. This is just it. That's our answer. That's the whole thing. Okay, so we took our base, right, which is 5, and that's where we start. Okay, so log base 5. And then we know that it's going to equal the exponent. So that's kind of the next thing that we look at, right? So the exponent's 3. So this is going to equal 3. And then sort of our leftover number is 125. So the 125 goes here. And that's it. That's what you're doing. Okay. So in the next one, it's slightly confusing, maybe, because it's written like the wrong way around. So we're used to having base to the exponent equals the answer. Well, this is like answer equals base to the exponent. So you have two options. Okay. One option is that you can like scratch out this 729 equals and move it over here, 729. Okay. But a better option, so you can do that, like if you really need to do that, go ahead and do that. But a better option is just to make sure that what you're paying attention to is not like what comes first and second and third and what's on the left and what's on the right, but like the sort of the roles that these things play. Okay, so I'm gonna have log. Okay, and I know that the first thing I'm always, that's an A. Why did I draw an A? Okay, so I'm gonna have log, and then I know that the roles that this is gonna play, maybe if my thing will work. Okay, so log, and then I know that the next thing that I'm always going to put is the base. Okay, so I'm looking for what is the base of this exponential expression. Okay, so the base is whatever's raised to the exponent. So in this case, the base is 1/9. So the base of my logarithm, the little number down here, is 1/9. Okay. All right, and then I'm probably going to look for my exponent next. You don't have to do it in this order, but I recommend doing it in this order so that you're always doing the same thing. So the exponent is -3. So that tells me that my logarithmic expression is going to equal -3, right? So let me color code this as I go too. And I'll color code it at the end. That's fine. Okay, and then finally, I'm looking for my answer, okay, which in this case is 729. And so that's what's going to go right here. Oops, that didn't switch to the other thing. 729 goes right there. So you can see again, right? So I started with my base. I started by writing the word log is actually what I started by doing, which is what you should do. And then the base is 1/9. And then I know it's going to equal the exponent. So I put left some space and then put equals my exponent, which is -3. And then my number left over, that 729, is what I'm taking the logarithm of. And you can put this 729 in parentheses. So like if you are putting a log in the calculator, it's probably going to pull up parentheses like as soon as you start to try to do it. Hopefully, like you can see, you're just moving things in specific places. All right, so for example 3, it's a little tricky because we have 10 and 10, and that kind of is confusing. So go ahead actually and make this 100. Okay, and if I make this 100, then think about this for a second. Does 100 equal 10 to the first power? No, 100 does not equal 10 to the first power. That's a dirty, dirty lie. 100 equals 10 to the second power. So if I make this 100, I have to make this squared so that it is now still a true statement. Okay, so just switch this problem around, make it be 100 equals 10 squared. Okay, so again, we're kind of, things are sort of in the opposite place, right? So our answer is first equals b to the x, okay? So first I start off by writing the word log. And normally the next thing that I would do is I would put a little 10 down here, except I am not going to do that. So 10 is the default base of logarithm. Okay, so there's an invisible 10. okay? So my base is invisible. So it's sort of like if you have, so that's this 10 right here, right? 10 is the base, okay? So there's an invisible 10 there. So the reason for that is because we live in base 10, like the digits that all numbers are made of are 0 through 9. There are 10 of them. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, and then after that, you just put 1 and 0 next to each other, and now you have the next number. So all of the numbers are made up of those digits just put into tens places, right? Okay, so it's our sort of default. And so that's why when there's no number with the logarithm, it's base 10. It's probably because we have 10 fingers. So people were originally counting with their fingers. So that's probably why we're base 10. Other bases exist. So like base 13 is what I think the Mayans used. Computers use base 2, just 0 and 1. There's lots of interesting stuff about bases, but we're going to ignore it. So just we use base 10. So if the base is 10, you don't put a number there, okay? So we're back to our actual problem. So let's start back over, right? So we write the word log. Instead of writing 10, we put nothing because the 10 is going to be invisible. But we are going to then put a space because then it is going to equal the exponent. All right, so our exponent is 2, right? Yay, 2. Okay, so since it's going to equal our exponent, it's going to equal 2. And then the last thing, our answer or our argument, however you want to say it, is going to go in our last spot right here. So notice there are no little numbers with the logarithm. So this is just log of 100 equals 2. Okay, so this is probably the trickiest kind of problem to do because one of the numbers that is in the original problem, the 10, doesn't appear in the answer here. Okay, so if you put in log base 10, I'm pretty sure the IXL will count it wrong. It's definitely not like a good thing to put in. So just if your base is 10, then life is slightly more confusing. All right, I'm going to be asking you for sure on the knowledge celebration what a logarithm is. So what is a logarithm? And you're going to answer that a logarithm is the inverse. I made that an I? I don't know how that happened. Okay, the inverse of a base. So just like subtraction is the opposite of addition, so it gets rid of addition, a logarithm is the inverse of a base, so it gets rid of the base, and you're left over with an exponent. Okay, and then the other thing that I want you to notice here is that you're not solving anything. You're not doing any math, you could say, okay? So when you do these problems, let me go ahead and put a square around that. When you do these problems, you're just rearranging. So far, you're going to end up solving stuff, but for right now, are you actually solving anything? No, just rearranging. Okay, and it's going to seem like we're going to like totally go off on a tangent here, but when we come back to 9, I promise that it'll make more sense, okay? So there's this magical number. It's about 2.718, and it just like appears all the time in things, in probability, interest growth, population growth. It also like has to do with like earthquake power. Like there's just all sorts of things where when you mathematically set something up to represent a system in nature, this number appears over and over, okay? So this magical number we call E, lowercase e, and it is approximately 2.718, okay? Just 2.71 is fine, or 2.72 or 2.7 even is just fine. There's an E button on your calculator, okay? And so then how this is related to logarithms, so what happens is this appears all the time as an exponential thing, and exponents and logarithms are related because logarithms get rid of the base of exponential expressions. So your sort of like statement here is if e to the x equals your answer. Okay, so if the base is e specifically, okay, e is not a variable. So this is important, not a variable. All right, e is a number. It's like pi. It's a lot like pi. So pi is a number, e is a number. So if e to the x equals a, then instead of writing log base e, we write ln. So natural log is what it's called, of a equals the exponent. So natural log means log base e of a, right? So that's what this means right here, but you never write log base e, you write natural log. And so this is just one of those things where like it appears so often in doing logarithms that instead of having to write log base e all the time, they just made a special button. It's so log base e is ln, which stands for natural log, okay? So this is, you probably want to write that down, natural log and that's ln. So if you look at a calculator will that has these buttons on it at all will have both a log button and an ln button, a natural log button. And we'll talk about the bases next section. Okay. All right. So now that you know that, let's look at these last three problems here. Okay. So looking at example 4 here. Okay. You have your base, which is e. And so you say to yourself, aha, if my base is e, then I am not going to write log base e. I am going to write ln. Okay. So that's just something that you'll need to remember. If you end up writing log base e, you'll just need to go back and fix it and turn it into ln. Okay. So log base e. All right. And then it's always of. So dude, come on, there we go. All right, and then so then we're looking at now the exponent, right? So remember the log always equals the exponent. Now, see how this is a little drunken equal sign, a little squiggly equal sign? That's because e, like pi, is an irrational number, so you don't get nice like whole numbers. I'm pretty sure that IXL will not count it wrong if you use an equal sign instead of this approximately sign, but you should use the approximately sign, right? So just like with the regular log ones, the log of something always equals the exponent, right? And then our leftover number here, the number we haven't done anything with yet, is this 20.09. And so that's what we're taking the natural log of, 20.09. Okay, so that looks terrible. This says that the natural log of 20.09 is approximately 3. That's what that says. Okay. So that is the answer. If you put ln 20.09 in the calculator, you're going to get something very close to 3. All right. So now let's go the other way. Okay. So here we're given a logarithmic expression and we need to move backwards. So you always start with the base, but the base is invisible here, right? Okay, so the base would be a little number right there. Since this is natural log, you say, aha, for natural log, the base is always e. Okay, that is always going to be true. If you have a natural log, the base is going to be e. All right, and then you go next to the exponent. Okay, so remember the logarithm always equals the exponent. So our exponent is -2. So we've got e to the -2. Okay. And then we put an approximately sign because we're paying attention and we're good. Okay. And so what number is left over? Well, the number that's left over is this 0.125. And so that's going to be what goes over here at the end, 0.125. So we have e to the -2 equals approximately 0.125. All right, so we're just going the opposite way from how we started. Okay, that's the answer. All right, for example 6, Again, we don't have the little number. We don't actually have a base here, right? So we're missing the base, which would be here. So if that was like, if there was a 3 there, then we would start by writing 3. But there's no base, but it's not ln, it's log. So anytime it's just log, remember the invisible base is 10. Okay, so you just got to remember that because you're going to like have to use that a lot. Okay, so 10, all right, and then now you're looking for the exponent. Okay, right, so base to the exponent. So the logarithm always equals the exponent. So the exponent here is 5. Okay, and then equals whatever number you have left over, which in this case is 100,000. Okay, so that's going to be our last number over here, the 100,000. And that is our final answer. Okay, so think about it as you're doing these, think about it as like structurally, okay, what is the base? What is the exponent? What's the number that's left over, or the argument, or the answer, however you want to think about it. Because that's really what's going to end up telling you how to do the problems, because they're going to give them to you in different orders. And so you have to kind of fill things in, and you might not, when you do the IXL for this, some of them you're just going to like fill in order. Some of them you're going to fill in only some of the numbers. And so you're not necessarily going to fill in like the leftmost box first and then like reading left to right. Start with wherever the like base is, exponent, number left over. And I would recommend always going in that order because then you're always looking for things sort of in that same order, and it'll help you a little bit, and it'll make it seem like the problems are a little less different from each other than they might seem to be. Okay, all right, you should be good to go to do the IXLs now. So enjoy.